Statistics of parking functions on labeled forests. That's also a classical question in this community.
Okay. Oh. Yes. Okay. Hello everyone. So, wait, let me see what time it is. So welcome to the 5th installment of Stefan Wagner lecture series at AofA 2024. I'm going to tell you something about parking functions related to labeled forests today. So parking functions is a topic I've been working with for several years. And I should say that I'm very happy to get this project with Stefan, because originally I had this question about parking functions with Richard Stanley that we could not solve. And I met Stefan last year at AofA, and I told him the question, and magically this happened. So yeah, so I felt like techniques in this community could resolve some problems that were unsolved using techniques in other communities. This is truly amazing to me. So what is a parking function? Here we are looking at the standard one-dimensional version. So we have n spots aligning the spots on a one-way street. And then we have a line of m cars entering, and then with m less than or equal to n, and every car has a preferred spot. If the spot is open, the car will just directly park there. And if the spot is not open, already occupied, the car will drive forward to park. And then if there is a spot that is available for the car will park, otherwise the car will leave the street. So here I give you a simple example. When we have the same number of cars and same number of spots, you see that for n equals 1, there is only one parking function with preference 1. And then when n is 2, it's 1, 1, 1, 2, or 2, 1. And then say if you have 2, 2, it's no longer a parking function anymore, because the second car will have to leave the street. And then for n equals 3, there are 16 parking functions. So from this pattern, people notice that the number of parking functions is given by m plus 1 to the m minus 1. And then more generally, when m is not equal to n, the same number of parking function coincides with the number of certain forests. So that is written here. And then this combinatorial coincidence motivated a lot of work, at least in the earlier years of study of parking functions, because like for combinatorial people, like if the cardinality of two very different objects coincide, there must be something more going on here. And let's first look at this question from the parking function perspective. There is a pigeonhole principle according to the parking algorithm, saying that if we have the number of parking function, the number of cars with preference less than or equal to I is greater than or equal to m minus n plus I for every I from n minus n plus 1 to n, it will be a parking function. And by a switch of coordinates, we can visualize this as forming the weakly increasing rearrangement, and then check if the order statistics are respectively less than or equal to n minus n plus I. So, and also from these, we have some immediate and less immediate observations. The immediate observation is that the parking function is invariant according to the order permutation, because if it's all about the pigeonhole principle and weakly increasing rearrangement, whether it's 1, 2, or 2, 1, it doesn't really matter. And also, we know that particularly if you change the preference of the car that is in 1, 2, up to n minus n plus 1 to any number within that set, it doesn't really matter, because here it's all about, it's all about this less than or equal to I for I starting from n minus n plus 1. And this will motivate a definition of parking functions that we will talk about very soon. And then a less immediate observation is that we can actually decompose a parking function into two parts. One is an arbitrary function to n minus n plus 1. And then the other is by doing some subtraction and translation, the remainder part of the parking function will be mapped to a smaller set of parking functions with m minus s cars and m minus 1 spots. All right, so, and then in our derivation, there is a central idea behind that, which is called the circular symmetry. Circular symmetry idea was motivated by Pollock quite a number of years ago, I should say many decades ago. And then the idea is that if you wanted to study parking functions, instead of looking at the one dimension, you can think about it as a circle. And then you can think that the exit of the street is also a spot on the circle called spot m+1. And then you can do rotation of the car preferences on the circle as long as spot m+1 is not occupied. It's a parking function. Equivalently, it means that no car will leave the street, go to the street exit m+1. And then, so here I also drew picture illustration for this. I guess I should probably put pi n instead of pi n. But yeah, like as long as m+1 is available, it's a parking function. And then, so this idea from Pollock could be used to, for example, derive the number of parking functions. It gave a very easy proof. But then what we did one step further is that we don't just look at all the car preferences afterwards or the spots they occupy. So it's like we think about it as a dynamic process. And every time a car enters, we try to check the statistics and see, okay, is a car available to park? Is it producing repeats? Is it lucky? And so on. And this turns out to give a range of new ideas. Okay, so now let's look at the first theorem in parking functions. And then, so this is the theorem. We are going to look at the generating function with respect to a statistic called SLEV, stands for size of level set. And then the other one is called leading element statistic. So this SLEV statistic generalizes the widely studied one statistic for classical parking functions, where you have the same number of cars and spots. And then this one statistic, there have been lots of study about that, and then people have studied statistics, and then the distribution, asymptotics, and many other things. But then this SLEV statistic was a new statistic. And then as you can see, we check the number of cars with preference in the range 1 through n minus n+1. It's partly motivated by the observation that I talked about earlier. And then it's also not surprising that this SLEV statistic reduces to the one statistic when n equals m. And then this leading element statistic is a new statistic that Richard Stanley and I discovered in our earlier paper last year. So it turns out that this statistic was equidistributed with one statistic, which I will talk about more later on. So when Richard and I did that work, we just found it's equidistributed through some generating function techniques, but we were never able to fully understand why it's equidistributed, because it's just so mysterious. But then through the work with Stefan, suddenly the mystery was resolved. Anyhow, so let's look at this. And first, I will provide an equivalent formulation of this in terms of the number of parking functions. So we can easily go from this one to this one using standard generating function techniques. Right? And then we can either prove the theorem in this generating function or in this equivalent formulation. I'm going to prove the theorem in this formulation, and then for the tree counterpart, I'm going to prove the theorem in this way, and then for the tree counterpart, I'm going to prove the theorem in this way, just for some variation. Okay. And then also let's look at some immediate corollaries. I will not provide proofs for time reasons, but then once we have the generating function, it's easy to deduce some standard probability facts, like the leading element statistic satisfies Poisson distribution when M scales linearly according to N. If M does not scale linearly, that's still an open question. We don't know yet. And then S-lab statistic can be standardized into a normal distribution. Okay. All right, so let's look at the proof. And then the proof is that we are going to classify into two cases. That is whether the first car prefers a spot in 1 through n minus n plus 1, and whether it is not in n minus n plus 1. Because as you can see, S-lab statistic is what we are interested in. And then whether the first car has a preference there or not also will matter for us about the leading element statistic. And then one observation is that if we count the total number of parking functions with preference in this, it's given by this formula. And then you can see from the formula above to below, we only multiplied by n minus n plus 1 because of symmetry. Okay, so now let's first look at the case when pi 1 is not in this set, and then I provided the reasoning for every one of the factors appearing here. I don't know how illustrative they are, but like, so x to the s indicates the fact that the S level set statistic is given by S. And then my sum goes from 1 to m because I assume that my first car prefers a spot here. So I know that at least it should be 1. And it could be m if all cars prefer a spot in the set. And then m minus 1, choose s minus 1, because I know there are s cars prefer a spot in there in total. So the first car already prefers this spot, and I just need to choose s minus 1 cars that prefer a spot there. And then the other factors need a bit more calculations and the explanation. So because like the first car prefers a spot in 1 through n minus n plus 1, and we do not really know which one it is. So it's n minus n plus 1 choices there. And then for the later s minus 1 cars that prefer those spots, we then, because we have already fixed the leading element to be a particular choice there, then you only have 1 over n minus n plus 1 possibility of coinciding with that. Then you know it's a like binomial distribution here, like it's 1 and then remaining n minus m choices, and then you think there are s minus 1 car there, and then y comes from the leading element, and then so on. Yeah, and then the last effect.
Y photo?
Where?
So y count the number of the counts that.
Yeah. So yeah, sure. So y is the number of cars with the same preference as the first car.
Okay.
Yeah, thank you. So, and then the last factor here is the decomposition that we talked about earlier. So now the remaining cars can be translated into a parking function. And then we have this formula. Okay. All right. Then the next also, and then you just apply some standard binomial calculations. You will get a little bit simplified formula here without the summation. All right, so now let's look at the second case. If the first car's preference is not in 1 through n minus n plus 1, then still we have x to the s because that's a level set statistic. And now the sum starts from 0 to n minus 1 because it could be that no car, yeah, so none of the remaining cars. So yeah, just something. So n minus 1 choose s means you choose s cars out of n minus 1 cars, and then here it's like n minus n plus 1 choices for this spot of the car. And then here it also comes from the decomposition, but then we take into consideration that So it's like combining two perspectives. So we have 1/m choices. So yeah, the two cases are similar, but there are some like subtleties we need to pay attention to. And then again, by standard standard binomial calculation, we can get rid of the summation sign. So this is a proof in terms of the generating functions. All right. So now here is the thing that I kept talking about the mystery. So if we take n equals m, then we notice that the S left statistic reduces to the 1 statistic, which is widely studied. And then it turns out to be equidistributed with a leading element statistic, which was never studied before. So when we found this out, we were like, wait, this is so mysterious because the two statistics are totally of different nature. Like the 1 statistic does not matter how we permute the car. The 1 statistic will always remain the same, but then the leading element statistic will not be the same always. But then the leading element statistic matters when we talk about the circular rotation, and the 1 statistic got changed. So like, how can it be? And then Richard and I tried to build an explicit bijection between these. We thought it would be very quick, but then we tried many different methods from algebraic combinatorics, I should say, refinement and everything. Nothing worked. So like, and then I met Stefan and he was like, wait, let's look at trees. I mean, trees is a classical topic for the community here. And turns out it works. And then it not just works, but also like the two statistics that are completely of different nature suddenly become statistics of the same nature. So one statistic, right. For m not equal to n, we don't have equidistribution, but we also have a corresponding formula. Yeah, thank you. So for this one statistic, as people probably already know, it's a root degree in a tree. And this leading element statistic also becomes a degree statistic, not for the root, but for a fixed, it's like a movable root. It's like it's always a parent of vertex 1. And I guess I should also mention, you don't necessarily need to look at the leading element. You can also look at the next leading element and so on. It will be the parent of vertex 2 and vertex 3 and so on. So then these statistics are of the same nature, and it's more reasonable that they are equidistributed. Okay, so I don't know if I have time to go over the BFS algorithm fully, but let me just mention a little bit. So we found out that via the BFS algorithm, which was pioneered by many experts back in the 1960s, I think. So, but at that time it was built for, so it was pioneered by Fuad and Riordan back in the 1960s. So at that time it was applied for trees, but then it can be generalized to forests. And it turns out that, yeah, that's what I was writing down here. The number of times pi I appears coincides with a degree, and the number of times 1, 2, and up to n minus m plus 1 appears also coincides with a degree. And then I actually gave a quick proof, but I guess I'll just go over it real quick because I don't have much time remaining. All right, so here is the proof. If you are interested, I can tell you more details later. So the idea is that we can build a cyclic function representation for every tree. So you just need to list the vertex number, and then you look at its parent, and this will give you a cyclic representation. And then through the cyclic representation, we can do a breadth-first search, as in computer science. And then for this breadth-first search, we can write down. So it's actually not that difficult. It's just you read the roots, and then you read all the vertices in level 1 and then level 2 and so on. And then if they have a common predecessor, you read the number from small to large. If it's different predecessor, it's about the predecessor number. And then from this, you can also do a tree specification and the forest order permutation. And then it turns out that the forest specification and order permutation coincides with the specification order permutation for parking functions. And I gave the definition here. So yeah, so for parking function, what we do is that order specification is easy. You just check for every number how many times it appears. And then for specification, you first form the weekly increasing rearrangement, and then you check the order where each digit is. And then we can also go back and forth between the two representations. So yeah, so we can also get a parking function once we have the specification order permutation, and then we can recover it. Okay, so yeah, continuing from the previous slide, when we have the tree, we can map it to a parking function just by mapping bijectively the order permutation and the specification. And then we can build a parking function. This is a parking function that will be resulting from the tree. Okay, so turns out, so this is the explicit bijection combining the two perspectives, and this is the formula. And then from the formula, you can see that the theorem is easily derived. So from this formula. All right, so, and here we also prove this, that generating function we saw earlier directly in terms of trees. And then, as I said, the S levels, the level set statistic will become the total degree of all the roots. And then the leading element statistic will become the degree of vertex 1. And here by degree, we mean the degree in the tree context. Oh, thank you. Thank you. Yeah, yeah. Thank you. Yeah, I'm not a tree expert, so. That's why I need to give talks here to get all the names correct. And then there is also that equivalence formulation, okay? So for variation, now I'm going to prove the theorem in this context, okay? So the idea, I should say, it's all step following. It's a very cute idea. It's that, and also like the corollary as before, okay? So the idea is about vertex splitting argument. I think we also saw this idea on Monday's talk. Yeah, those Taiwanese groups. So like the idea is that because we have the parent of vertex 1 and we have vertex 1, so we are going to first think that it's a distinguished vertex merged together, and then we are going to split the vertex. So this is a key ingredient here. And then we also use Cayley's formula in here and there. So let me first show you the picture. Here is the picture. So the idea is that I have all these forests, and then I have this distinguished vertex P, and then I have, I will split it. And then once I split it, I will have this original vertex 4 as the child of vertex 1. Oh my God, I'm drawing out of time already. Okay, and then I will put all these as, so I don't know if people can see that. So yeah, like I have vertex 1 and then vertex 4 here. And then I have this Y branch. I also put it as, oops, the child of the parent of vertex 1. And then I put the other things as a children of the root. And then here is the explanation of why this works. How much time do I have? Okay, 3 minutes. So because it's 3 minutes, I'm not going to go through this in detail, but like, yeah, if you are interested, I'm happy to show you about this more. So it's just about splitting, and we also need to differentiate into 2 cases, and then, yeah. Okay, so the last thing I want to show people is this. So once we know that they are equidistributed, obviously we wanted to know, is there a way to build an explicit bijection? And as I said, it's actually still open if we can build a bijection directly in parking functions, and there are still other open questions also, but then at least we can build a bijection directly in the context of trees. So here is the algorithm. We are going to remove the edge connecting vertices 1 and p, and then we connect vertex 0 and 1 by an edge, and then we interchange vertices 1 and p. And it turns out that this is also an involution, and also the degrees of all the other vertices also are preserved. And here is a picture illustration of what we are doing. And then like the tree structure is like going from this tree to that tree. And then once you go from this tree to that tree, using the BFS algorithm, you can also go from one parting function to the other parting function. And then the ones pi and leading pi statistics are interchanged, and many other statistics are preserved because of the involution structure. All right, so now I'm done. Thank you so much. Thanks.
Questions?
Okay.
Yeah, I just wanted to ask, at the end, you say it's still open if you have a bijection directly on parting function,
Right.
but you kind of have, no? I mean,
No, what I meant is that, so here we did build a bijection between parting functions, but we have to go through the trees.
and you don't, but, okay.
I was wondering like if there is a way to directly build a bijection within the context of parting function. Without me,
Without the tree.
yeah. So yeah, it's still open, and I can tell you, Richard and I tried every method we could think of. We thought it's an easy question, but no, yeah. Mhm.
Questions?
Still.
So the statistics are equally distributed if m equals n,
Right.
but can you kind of generalize the statistics for m less than n and find a pair of statistics
For
that are equally distributed?
so I mean for m less than n, the S lab statistic is like not the same as the leading element statistic, but it could be possible. It's also the sum of some other statistics. Yeah, so
Like generalize the leading element, something that would be.
I mean, it's
Like-
possible. We need to think about this more, but it's possible because like here we are only looking at the leading element. There are next leading elements and stuff. So possibly there are some sum and stuff.
Okay, like the m minus n leading element. or something.
Yeah, it could be. Yeah,
Okay.
thank you.
Is this bijection
Mhm.
going through the trees suggesting new statistics for parting functions?
Yeah, so I mean, definitely this is something I want you to know as well, because like, I mean, for parting functions, when we discover those two statistics, there are no relationship at all. But then for the trees, they both become degree statistics. And then there are other statistics in trees that we do not know what they correspond to in parting functions. And there is also statistics in parting functions, for example, luckiness, that I do not know what is the corresponding one in trees. There are many open questions out there.
Okay, so thank you very
Mm.
much.
Thank you.
We go for the last block of functions.